Hello, and welcome to Earth Science Planet Earth Lab. In this lab course, we will aim to explore the different Earth systems and how they interact. What factors create and influence the behavior of Earth systems, how have the systems changed through time, and what effects humans have had on their behavior. Generally, this course is designed to help you develop an appreciation for the complexity of the Earth system and better understand your place within. Since most of you listening are most likely not pursuing a degree in the science field, we want to simply get your feet wet into the many areas and fields of earth science. Before we begin into course material, let's quickly discuss how labs will run each week and what is expected of you in this course. You will find all the following information detailed in the syllabus. Each week, lab material will be released on Garmin the Sunday before each week begins. Under the lab module for each week, you will find a pre-lab reading, an additional resources page with helpful links and a reference lecture, a lab quiz, and any other resources you will need to complete the activity that week. I strongly recommend taking a quick look at the pre-lab reading before you come to class. It is a helpful document that will summarize the basic information of each lab. Lab quizzes will be due each week at 5 p.m. on Friday. You are responsible for completing the lab during your scheduled class lab time. Each lab will require in-person participation within the classroom and the completion of the quiz. Each week you will need to arrive on time to lab and sign in so the TA will have a record of your attendance. Food is not allowed within the lab rooms, but drinks are allowed as long as they are capped. All lab classrooms will adhere to the university guidelines regarding all COVID policies. Please come prepared. You will need to bring a laptop or your iPad to class each week to submit the lab quiz. Phone usage is not allowed in the lab and will not be permitted to complete the lab quiz. Labs will be graded each week by your TA. All labs will be weighted equally and there are no dropped lab grades. A student will not receive credit for completing the lab without showing up to class. In the event a student is not able to attend lab, a fully online lab will be available as a replacement and must be completed the same week as the in-person scheduled lab, unless extenuating circumstances arise. In order for a student to receive the online quiz, they must contact their instructional lab TA, explain the reason for their absence, and will be given an access code to the online quiz. Failure to contact a TA regarding an absence will result in a 0 for the week, with no exceptions. Labs close at 5 p.m. on the week they are listed on the schedule. In general, no extensions will be granted and late work will not be accepted. You have multiple days to complete the lab outside of lab if you need more time. Plan accordingly. If you are experiencing technical difficulties, please email your TA or the head TA and explain your situation. However, if you email the day a lab is due regarding issues, do not expect a response or an extension right away. Start early and attend office hours if needed. If any issues arise during the week, contact your TA as soon as possible. We are here to help and want you to succeed, but we cannot do so unless we are informed. With that in mind, please allow 24 hours for a response before you contact your TA a second time. If you are a student with a disability and require accommodations, please request those as soon as possible through the head TA and correct services. Check the Garmin page for information on how to reach the head TA. Check the syllabus for any more detailed information about the lab workings and expectations. The idea behind science and the process of the scientific method is that while there are statements of actuality or occurrence from direct observations or evidence that can be verified, otherwise known as data, science is not a collection of facts or answers. Science is a never-ending cycle that can disprove various concepts, does not always prove a concept, but always must be able to test a concept. Science comes from natural human curiosity, gathering info and testing the data. In the end, facts and information must be verifiable and tests reproducible. Every branch of science uses the scientific method. The scientific method is defined as a procedure consisting of systematic observation, measurement, and experiment, and the formulation, testing, and modification of a hypothesis. People are accustomed to hearing about the scientific method within the science field throughout most of their education, as well as in new understandings or findings in our everyday life. Often we hear news reports about scientific findings, explorations into space, the understandings of an infectious disease, or a discovery of a new fossil. In order to properly use the scientific method, a combination of observable facts can be implemented to give rise to a hypothesis. A hypothesis is an idea that predicts the outcome of an experiment or explanation about an observed phenomena in the natural world. For example, the ancient Greek scientist Archimedes observed the water level rising when he got into his bathtub, which led him to hypothesize that his body was displacing a certain amount of water. After a hypothesis has been stated, experiments are required to test it. Archimedes dropped various objects into his water-filled bathtub and found objects denser than water sink and objects less dense than water float, but both will displace an equal weight of water in relation to the object's size. His experiment gave rise to his conclusions, or a statement based on experimental measurements or observations. Today, we know Archimedes' principle, which explains that the buoyant force of an object is equal to the weight of the displaced water and is an important part of physics and fluid dynamics. The scientific method is a never-ending cycle, as you can see from the diagram on the right. It is not a straightforward process and often involves loops and double backs, readjusting and reevaluating the hypothesis and the data that is collected. Beyond a hypothesis, which we have already discussed, scientists have terms for other concepts, such as a theory or a law. A theory is a hypothesis that has been tested and shown to work in many different situations. Einstein's theory of relativity is a common example, an explanation for how the laws of physics apply to non-accelerating observers. The scientific use of the word theory is not to be confused with the common usage of the term, as in, I have a theory about this, or it is only a theory. True theories are structures of ideas, tested multiple times that explain and interpret facts. A law is an identified relationship among observed phenomena, such as the first law of physics, F equals ma, or force equals mass times acceleration. Most of science is based on theories, which are the basis for entire branches of science, such as the theory of evolution or the wave-particle nature of light in physics. Unlike the United States, all branches of science use the metric system for measurement. Most countries in the world use metric units, and this system enables scientists to share data easily across nationalities. The metric system is based on multiples of 10 for the unit conversions, a much easier route than the imperial system the United States uses. All metric units have a root unit that can be preceded by a prefix. The prefix changes the size of the unit. For instance, when measuring length, the root unit meter is used. Also, the root units of liters for volume, grams for weight, and degrees Celsius for temperature are used in the metric system. In the chart, you can see that the prefix centi means that it would take 100 centimeters to make up 1 meter. Likewise, the prefix kilo means that there are 1,000 of the root unit meter in 1 kilometer. You may be familiar with words like gigabytes or megahertz in your computer. That also contains metric prefixes. The table you see shows some common base units and the prefixes corresponding. Because there are multiple systems of unit measurements, sometimes it is necessary to convert from one system to the other. The table shown provides a few examples of common conversion factors. To keep these numbers and units straight, we set up a relationship with the given quantity in units on the left and the desired units on the right. Between, we set up the relationship to convert to the desired units by the process of cancellation of units. We also calculate the numerical values associated with each unit in the relationship. Pause for a moment and try the examples in front of you. Now that we've covered our science basics, if you will, we will move on to our first earth science topic, plate tectonics. One of the most important discoveries made through the use of the scientific method was the theory of plate tectonics. In 1912, Alfred Wegener, a German scientist, proposed the continental drift hypothesis. Wegener noticed that the continents fit together, sort of like a jigsaw puzzle, with the most notable being South America and Africa. There was also evidence of terrestrial fossils of similar species located far apart on different continents, as well as the distribution of geological features such as mountain ranges on those continents as well. He hypothesized that all of the modern-day continents had previously been pushed together in a supercontinent he called Pangaea. Wagner suggested that over millions of years, the continents had moved apart. However, he had no evidence to support his hypothesis and did not have a physically plausible explanation for what caused the movement. Unfortunately, his thoughts were widely ridiculed, and Wagner never lived to see his theory accepted. He died at the age of 50 while on an expedition in Greenland. Decades later, in the 1950s and 60s, the idea of continental drift resurfaced. Shortly after the conclusion of World War II, sonar-equipped vessels crossed the oceans and collected ocean depth profiles of the seafloor beneath. Three-dimensional relief maps of the ocean floor were created. Marie Tharp, an American oceanic cartographer, made the first of several maps that revealed the presence of an underwater mountain range more than 10,000 miles long in the Atlantic, otherwise known as the Mid-Atlantic Ridge. Tharp hypothesized that mid-ocean ridges appeared to be the extensional rift valleys formed by plate motion. The concept of seafloor spreading was proposed by Harry Hess in 1960. Hess hypothesized that molten material in Earth's mantle was continuously upwelling along the crests of deep-sea ridges, and as it cooled, it pushed away from the ridge's center, creating a successively younger ocean floor. The flow of the seafloor material was thought to bring about the migration or drifting of the continents. Further investigation into the theory of seafloor spreading led to the discovery of magnetic banding on the seafloor. Around 1963, Frederick Vind and Drummond Matthews used electronic magnetometers to survey the ocean floor and found a very consistent striping of normal and reverse magnetic polarity in the seafloor rocks. These stripes occurred in parallel bands radiating outward from the mid-Atlantic ridge as more molten material upwelled from the ridge. During times of normal magnetic polarity, the rocks being created stayed normal. If they were created during times of reverse polarity, the rocks would freeze that magnetic orientation in place. It was quite a revelation and changed the face of geologic thought. Today, the seafloor stripes can be used to calculate how fast the plates are moving on top of the Earth's mantle. There were a number of scientists that came before and after the aforementioned discoveries, each with their own idea or contributions. Once the mechanics of how the plates moved was understood, three types of plate boundaries were defined. Convergent boundaries, where plates push against each other. Divergent boundaries, where plates move apart. And transform boundaries, where plates slide past each other. Each type of plate boundary has different notable characteristics and geologic features. Next week, we will explore more in depth how the plates move, the specific characteristics of each boundary type, and some more details about plate tectonics. For today, all you need to remember is that there are three types of plate boundaries, each with their own motions.